Let us find all the cosets of the subgroup generated by 2 of our group here Z sub 12. So cosets are actually a subset of a mathematical group that will consist the results when we obtain a fixed element of a group, or multiplying a certain or operating a certain fixed element of a group by each of the elements. Now here we are going to look for the cosets of a subgroup generated by 2 on the same set Z12. And since we're talking about here all cosets, so we are going to provide here both right and left cosets. So here, let's start with our group. Our group here is Z sub 12. Now these are the remainders when we divide the n integers modulo 12. So the elements here are actually 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And for 12, since the remainder when we divide 12 by 12 is 0, so it's already represented here. Now this is for our group. We are asked here to find the cosets of a subgroup generated by 2. So let's try to determine the subgroup generated by 2. So we will start with, of course, 2. Now, since this is on what we call one Z12, or we are talking about addition modulo 12, so 2 plus 2 is 4. 4 plus 2 is 6. 6 plus 2, 8. 8 plus 2, 10. 10 plus 2 is 12. That's actually 0 modulo 12. And you will just have this because 0 plus 2, you will just return to the first element here, 2. Now this is our subgroup which is generated by 2. We have the a set here, or a subset of Z12 with 6 elements. Now we are talking by the way, we are asked here to find all the cosets of this subgroup that is part of Z12. The cosets here will result if this would be our H, which is the subgroup of our Z12, all the left cosets will be represented with this A, H, which is equal to A multiplying all the elements of subgroup H. Okay? So that's the result. We're going to come up with all the elements that will result to this. For all A, which is actually which is in this case, all A here is element of Z12. Okay, so we're going to look for all the cosets, the result of this on the same operation, the addition modulo 12. Okay, so our H here, let me just write this in. I would like to rearrange all the elements. I would start with 0, 2, 4, 6, 8, and 10. So we are going to operate this with all elements of our Z12. So let's start with, of course, 0. Okay, so if we have here 0 plus, because the operation here is H addition modulo 12. Okay, so plus H, you will have here the results. The same results, 0 plus 0 is 0, 0 plus 2 is 0, 0 plus 4 is 0, 0 plus 6. We're adding 0 on all the elements of H. 0 plus 8 is 0, 8 is 8, 0 plus 10 is also 10. Now this is the first left coset. It's called left coset because the elements here are placed before our subgroup here. Now if you're going to move to the next element of Z, which is a Z12, which is 1, so 1 plus our H, so that's 1 plus the first element of H is 0. 1 plus 0 is 1. 1 plus 2 is a 3. 1 plus 4 is 5. 1 plus 6 is 7. 1 plus 8 is 9. And 1 plus 10 is 11. This is our second left coset. Okay. Now, let's continue this to the next element of our Z. Okay. So we have 2 plus H. Now, the first element is 0. So 2 plus 0 is 2. 2 plus 2 is 4. 2 plus 4 is 6. 2 plus 6 is 8. 2 plus 8 is 10. 2 plus 10 is 12. That's 0 modulo 12. Okay. Before we continue to the next few elements here, we can see that this left coset has the same result as this here. Now, the cosets must be what we call one unique in nature. This would mean that if we are going to use A, elements of Z12 being 0 and 2, you will have the same result because we could just simply rearrange all the elements here because they are under the same set. This is also true with F, 4 plus H, that F, that's 4, 6 plus H, 8 plus H, and 12 plus H. Because if we are going to start with this, okay, 4 plus 0 is 4, 4 plus 2 is 6, 4 plus 4 is 8, 4 plus 6 is 10, 4 plus 8 is 12, that's 0 modulo 12, and 4 plus 10 is 12, that's 2 modulo 12. This is the same set as this one here. Now, you might want to verify this on your own, but definitely, since we're talking about sets, we have the same results here. This would mean that for 0, 2, 4, 6, 8, sorry, this is not 12, but this is 10. Sorry, my bad. 0, 2, 4, 6, 8, and 10, they have the same left cosets. Okay? Now, let us continue with our number here. Let me use black color. What if I have 3 plus H? Take note that our H is this one here. So 3 plus 0 is 3. 3 plus 2 is 5. 3 plus 4 is 7. 3 plus 6 is 9. 3 plus 8 is 11. 3 plus 10 is 13. Under modulo 12, that's 1. Notice that this is also the same as 1 plus H earlier. This would mean that they are just of the same results. This is also true, and you might want to verify this. 5 plus H, 7 plus H, 8 plus H, 9 plus H, and sorry, again, 5, 7, sorry, don't have 8. Okay, so this is actually 9 plus H and 11 plus H. All of this will just give you the same result here. What would this tell us now? Now, for all the left, we're starting with left. Sorry, let me label it here. We started with left cosets. All the left, for the left cosets of the subgroup generated by 2 on Z12, we only have 2 unique cosets. And that is actually, we have here, this one here, we have the 0, 2, 4, 6, 8, and 10, which is just equal to 0 plus H, or etc, etc. Okay, 2 plus, let me just remove this notation so that we will not be confused with the other notations later. This is just 1, which is just the same as 0, 2, okay, 0, 8 plus H, 0, 2 plus H, 4, 6, and 8, and 10 plus H. And the second coset, left coset, okay, we have left coset is 3, sorry, let's not start with 3 because we have here this one here, 1, 3, 5, 7, 9, and 11. So we only have 2 left cosets. Okay, so since we are asked to solve for all cosets, so we are also going to show here the right cosets. So for our right cosets, okay, right cosets, with our H again, 0, this is our H, right? The set generated by 2, I'm just going to arrange it 0, 2, 4, 6, 8, and 10. So for our right cosets, it will look like this. You're going to have H and A. This means we're going to have to operate H times A for all H element of our subgroup here, and all A for all A element of our Z12. But if you're going to look into this, starting with the first element of our A, which is again first element of Z12, which is 0, you will have this form here, H plus 0, which is actually equal to your 0. So 0 plus 0 is 0, 2 plus 0 is 2, 4 plus 0 is 4, 6 plus 0 is 6, 8 plus 0 is 8, 10 plus 0 is also 10. This is actually the same as this one here. Notice we have the same results. This is because addition modulo 12 is actually considered as an abelian. Okay, meaning we have the property of commutativity for addition modulo 12. This means that we have the same results for our 0 plus h, our first left coset earlier. This is also true for h plus 1, the second right coset, which is just equal to actually the first or the second, sorry, the first, my bad, the second, we're talking about the second left coset as well, 1 plus h. Because if you do this, 1 plus 0 is 1, 0 plus 1 is 1, 2 plus 1 is a 3, 4 plus 1 is 5, 6 plus 1 is 7, 8 plus 1 is 9, and 10 plus 1 is 11. And this is also true with the rest, okay? This is also similar to 2 plus h, etc., etc. This is also true with 3 plus h, similar to the discussion earlier. In short, we also have two right cosets here. We have two unique right cosets. These are the two right cosets here. And as you can see, both the right, I'm gonna label this as our right cosets. Okay, this is our two right cosets. Because, okay, as you can see here, we have the first and second. We have the same left and right cosets because again, this group Z12 is an abelian, or we have the property of commutativity. And the idea of having only two left and right cosets is actually anchored to the idea of determining the number of, or the index of h in G, because the index of h in G is just equal to the number of left and right cosets using h on the same G. In this case, we have here Z12. Okay, we are going to have this in notation form. This is this one here, the index of h and G. The index of h and G is just equal to the index of our Z12, okay, which is actually number of elements in Z12, that's 12, okay, over the index of our h, which is, our h is this one here, a subgroup generated by 2, we have 6. So 12, let me remove these two equations here. So 12 divided by 6, you have 2. This determines the number of cosets. Okay? But in this case, again, because we have commutativity, the number of cosets here is true for both the right and left cosets. And similarly, they are actually the same cosets. So these are the cosets, all cosets, but we have the same left, two left and two right cosets for the set generated by 2 of our given, subgroup generated by 2 of our group Z12. Thank you very much for watching.